Okay, hello again. Last time we were looking at the problem x equals g of x in fixed point method, and our g of x function was cosine x. Now I just want to show you how in MATLAB you can very quickly write a little code to solve that problem. So let's move on to our laptop screen here. So what we're going to do, so actually if I just show you the diagram of where we're going at, on the right hand, this is g of x is cos of x, so that obviously goes to 0 at pi by 2, which is beyond 1, shown here. And we're looking just graphically for something in the region of 0.7, 0.8 as a solution. So we're going to start our iteration away from it as 0.4 and see where we get with our MATLAB. So of course this is one example you could do by calculator, but I would really encourage you to do it by MATLAB, as we're going to look at more complicated examples later in the module, and you really need to get to be familiar. So this is written out in your lecture notes, but first of all we start with x is 0.4, and that's our initial condition. I'm going to actually put some comments in here, even though it's at the command line. So this is, and as I say, if you're lacking confidence with MATLAB, I just keep away from doing programs, scripts for a while, and just do things at the command line until you get confident with the commands, and then go back to your scripts. So we start with x is 0.4, and then we'll start a loop for n is 1 to 10. So we're going to iterate this 10 times. So we're going to perform 10 fixed point iterations. Okay, so this is possible with the command line to put a loop in. You just have to complete it off. So that's the loop, and then the contents of the loop go in here. So we have we're going to then put in our fixed point iteration, which is simply applying the cosine function. So we're going to define a new value, which is xn plus 1 equals cosine of x. And we're going to put a semicolon under there to suppress the output. If you don't put a semicolon on the end in MATLAB, it just prints it out. It's not going to do anything wrong, it just will slow down the program, because there's sort of computational expense in printing to the output. There you are, fixed point iteration. And then we have x is x new. We're going to just swap x to the x new for the next loop. Okay, swap x and x new for next step. So these sort of swap things at the end of loops are very important to remember if you're using variables like this. So here we go, we swap x into x new into x, so that it can carry on with the iteration. And then we finish the loop, end loop, and that's it. So that's doing 10 steps for our iteration, fixed point iteration, round and round this loop, starting with x is 0.4. So if we just put in x, it'll give us a value which is 0.7337, which is very close to the root. We just go to its value. Now we can actually check that that's our root, because at the root x should equal to b cos x. So if we do cos x, it's 0.742. It's within a small error now of the correct solution. Okay, or f of x, which is simply cos x minus x, should be close to 0, yeah, which it kind of is. If you want more decimal places, by the way, you can change things like go format long, and I can then list what X is, and I get many more decimal places. If I go back to short, I go back to the standard default setting. So if you're looking to find differences in the sort of 6th, 7th decimal place, then look at that. Okay, but this is just a very simple way of doing your fixed point at the command line. Of course, you can put that into a code, no problem. You could just basically copy this into a script as well, and it would run fine. Okay, so again, this is how I'm going to use MATLAB. This term in particular is give you lots of template codes. I really want to make you understand the theory and how the theory feeds back into the code. A little bit less about the programming, although I'm happy to provide sort of the basic programming support in support of this module if required. Okay, so that's just our first with the MATLAB. So the next task then is to do convergence analysis for the fixed point, and there's a little bit more involved now with the fixed point method, and we'll make a start at it in this video, and probably carry on in the next. Okay, so let's get the board up now. Here we go. Okay. So we've just seen a very simple example. Now we want to do, as I say, probably the new bit for you this term. If you did this with John last time, it would have been quite sort of in passing, and we're going to just be a bit more rigorous about this of fixed point method. And before we get there, we need to set up a theorem. So the first theorem we used, it's not theorem rich in this module, but I wanted to show you that there are theorems in numerics. It's not just about punching stuff into a computer. There is mathematical basis and almost links into analysis. Even though that's not the aim of this module, I just want to show that that's the structure. And we had theorem 1, which was the intermediate value theorem that we needed for the bisection method. Now we've got theorem 2, and it's called the mean value theorem. And I'm stated like this: if the function f is continuous on closed interval AB and differentiable as well, on the open interval a comma b, because it's a derivative, we have the open interval, then there exists real called psi, which is in this open interval, such that the derivative because FB FA and B minus A. So what we're saying is that if you have an interval B and A, that the derivative somewhere in the domain is going to be equal to that constructed by using the values of function either side. Okay, so it's really it's plausible. We're not going to prove it, as I say, that I don't think that's the domain of this module, but to show that there's sort of theoretical and theorematic, I mean, I don't think it's a word, but theorem basis for this module is very useful. Just link it in with other areas of mathematics. But I'm going to sort of show you a diagram which, you know, at least gives the plausibility and is the basis really of probably writing the proof. So what we're saying is that so where we're going is with this is that the convergence condition for a fixed point will involve the first derivative. So we need to set up the first derivative sort of theorem based on that. Okay, so there's a little bit of building things up. So if we have a continuous differentiable function between a and b, and we construct the chord, okay, that the gradient of that chord you know, I'm going to make this a bit bigger and then we'll move on to a different one. Let's make it a bit bigger. So there's A, there's B, construct these points. So we construct the chord. So if you think this chord has gradient using the endy bits, so it's using f of b minus f of a, b minus a. Yep. Gradient this thing is f of b. So it's basically saying if you've got that chord constructed there somewhere in between, it's going to have the same. And we can see maybe if I took the tangent in this case, f prime cosine is actually, we can see that actually kind of that point there that the gradients are equal. Yeah, so f prime cosine. Now the thing about this cosine variable, it is often, we don't give it a specific value. It could be anywhere in the domain, and people don't like that uncertainty about it, but it's a very useful device for proving things about convergence laws, etc., etc. So x lies anywhere in our open interval okay, and that's all we need to know, but it's basically saying that somewhere the local tangent is going to be the same as the chord. Yeah, that's what the mean value theorem says. Okay, so that's a bit of background, an important background, so we can proceed with determining convergence rates. So that's the theorem. Theorem 2 is mean value theorem, and then we've got some definitions. So we're going to have, we'll call definition 1. So when, this is really just stating what we're doing, f of x is 0 is rearranged as x equals g of x. The fixed point iteration is given by x of n plus 1 equals g of x of n. So that's just restating what our method is. Definition 2 is a true solution. The true solution is when the fixed point method converges. So what we're saying is that x of n will tend to x of n plus 1 will tend to this thing called the true solution, x star. So we can then just restate a form of our fixed point method that x star equals g of x of star. Okay, so that's just saying that the line y equals x interxes into x. Okay. And then the most important definition is the third one. Sorry, not definition, theorem, which is our conditions for convergence, which we call theorem 3, which is condition for convergence of a fixed point. And that condition is going to then be, now in our Newton notation, g prime psi. So remember, psi is a variable that takes you anywhere in this domain, as given by the mean value theorem. G prime now is our first derivative of g. And we're going to say the modulus is less than 1, and where psi is in A, B, just restating what we did. Okay, so this is the key result that we're going to prove. So we are going to prove this because it's really is quite central. I don't prove the sort of more supporting theorems here, is that the gradient of G is going to be less than 1 for convergence. That's what's stating. And I think what I'm going to do is leave the proof to the next video, but just give you an example, or a couple of examples of where this might work and not work. So if I can go to my slides now. So we've got this theorem about the gradient less than 1. So this example in this slide here of example of g prime is less than 1. So a nice shallow gradient, very similar to the example we did with cosine. This is y equals x. And what we get, and these are diagrams it's worth getting used to, is that x is g of x. And I'll go into this again a little bit more detail next time. X equals g of x is these horizontal arrows, okay, and then you just complete the circuit with these other vertical arrows. So x is g of x is your first iteration, x is g of x is your second iteration, and it converges because it's spiraling, and this happens in quite a lot of cases. Not all cases of convergence, it will sort of cobweb like a little Spider-Man's web into the root, which is in the middle here. Okay, so that's kind of an example we did before. As g prime is less than 1, so that's a good basis that it might be worth. But when g prime is greater than 1, we get the method doesn't converge. So this is just giving you an intuitive background to this theorem that we'll prove next time. Okay, so you start off here, and the cobweb, instead of zoning in on the root, just gets further and further away, and it's all because the gradient of g prime is greater than 1. I put g prime x. I guess, strictly speaking, maybe the software I was using wasn't allowing x so easy at the time. Really, strictly speaking, we should put psi to be consistent with our annotation. So it's x anywhere in the domain, which is really what psi gives us. So you can see that it's going to be important, but the key thing is how we prove this. Well, the key thing is going to be using those definitions we wrote down, definitions of true solution, definitions of fixed point, and also using our mean value theorem. If we put those three things together, we should be able to get an error law that either converges or doesn't, depending on this g prime. Okay, so I'll leave it on that.